Hello everyone, welcome to the fourth lecture on cosmology. So, let us quickly summarize what we have learned so far in the first three lectures. We now know that the universe is expanding. It was clearly smaller in the past and hence hotter, the temperatures were higher. We also have discussed that the constituents of our universe are mostly radiation, the baryons, the normal matter, the cold dark matter which is also non-relativistic, and dark energy which we have no idea about. The different phases of the universe, of the expansion of the universe are the radiation dominated phase, the non-relativistic matter dominated phase, and the more recent dark energy dominated phase. There was also possibly a phase of inflation, a rapid expansion phase at very early times, but this is something which we do not understand very well. Now, we can ask the question that suppose we stick to the standard model for the time being, that is the radiation dominated, the matter dominated, and to some extent the dark energy dominated phases. Can we apply our understanding of fundamental physics, what we know, to this model, and then can we try to understand different types of matter, how they evolved, what they did, when they were formed, what will happen to our universe, and so on. Can we understand that by just applying the laws of fundamental physics to the cosmological model? Just remember, we are working under the paradigm of the hot Big Bang model. So, at early epochs the universe would be smaller, just what has been depicted in this picture, a smaller universe, and then it expands, and then various things happens as the universe becomes smaller and smaller. Now, a very basic principle which we will try to use while describing this hot Big Bang model of cosmology or the early universe part of it is that when the temperatures are high, it becomes more and more difficult to form stable entities. For example, take nuclei, take a helium nuclei or any other nuclei you can think of. We know that they are all there, all around us. But if I go back in time and make the universe so hot that the energies becomes very high, and this can disintegrate this nuclei into individual protons and neutrons. So, at very early times when the temperatures are hot, it will be very difficult to form even the nuclei. You can take the same example and then argue that the same thing will happen with atoms as well. Even when you form nuclei, you may not be able to form neutral atoms because the electrons will be very easily liberated from the nuclei if the temperatures are too high. So, keeping this in mind, let us try to list some of the major milestones in our universe. So, what I have done here is listed the events, the time at which we believe they have occurred, time starting from the Big Bang, at least to the order of magnitude you can take these times to be what they are, the corresponding redshifts, this you can of course convert to the scale factor or the size of the universe, and the corresponding temperatures in units of electron volts. So, you can go through this list. What I will try to do is I will try to highlight some of them one by one. Let us start with inflation. So, we have already talked about this. This is expected to have occurred very early in the history of the universe. Let us say the age of the universe would be somewhere between 10 to the minus 36 to 10 to the minus 32 seconds. This is something we discussed in the previous lecture, and we also think that this is the time during which the perturbations in the density field were generated. Something interesting would have happened which is called baryogenesis, and that is something very important for our universe. So, imagine the universe right after the Big Bang. Now, if they contained equal amounts of particles and antiparticles, then what will happen is we expect them to annihilate and the resulting universe will be simply dominated by photons, by the radiation. However, we know that we find the matter to be overabundant compared to the antimatter in our universe. We find matter in our universe, we do not find that many antimatter. So, the main aim of this baryogenesis models is to explain this observed baryon the matter antimatter asymmetry through some mechanism without assuming any initial asymmetry. So, it should come, there should be some mechanism which will give rise to this asymmetry, and that should then explain the observed amount of matter in the universe with respect to the number of photons we see. There are many models, many paradigms, but none of the models are kind of constrained or singled out by experimental tests. When the temperatures came out to be around 100 GeV in the universe, the electroweak force will actually break, so to speak, into the usual weak and electromagnetic interactions, and that this is the time the fundamental particles in the standard model of particle physics acquire their masses through the so called Higgs mechanism. So, that would happen around something like 10 to the minus 11 seconds after the Big Bang. Then we will have something like the quantum chromodynamics phase transition or the QCD phase transition. This would happen somewhere around 100 MeV. This is the time the quarks and gluons will get bound and will form protons and neutrons, which will eventually form matter which we are made of. At some point there will be dark matter freeze out. What happens is, at early times the dark matter particles, of course we do not know what they are, but probably they are something which are beyond the standard model of particle physics, but probably having only weak interactions. Clearly they cannot have electromagnetic interactions, so that those particles are ruled out. And one believes that the dark matter particles are only weakly interacting. So, at early times they would be interacting with the rest of the matter, but after some point they will kind of decouple and would freeze out, their abundance will not change after that, and that is the dark matter which we observe today, and that we expect to happen somewhere around an energy scale of MeV. This value of course depends on what dark matter particles are we talking about. So, this is very uncertain, so I have put question marks here. A very interesting thing happens around 1 second after the Big Bang. The neutrinos before this time would have been interacting with the primordial particles, with all the other particles through weak interaction. At some point their interaction rate will go down because the densities will go down and they will decouple from the rest of the matter, and then the neutrinos just remain as they are. Okay? Their temperatures decrease because of the expansion of the universe, but they do not interact with any other matter. This decoupling happens when the temperature would be around again 1 MeV, 0.8 MeV or so on, okay, 1 seconds after the Big Bang. The next thing which is quite interesting is that is the annihilation of electron positron. So, before this time the universe contained both electrons and positrons, but probably slightly more electrons than positrons. That would happen somewhere at early times. We need matter to be more than antimatter, but whatever this is, the electrons and positrons would keep on annihilating, and at some point the remaining positrons annihilate completely with electrons, and the energies get transferred to the photons. Basically they produce radiation, but not to the neutrinos, because neutrinos would have decoupled. We will see its implications soon. 3 minutes after the Big Bang is the time when you expect the first nuclei to form. Before this time, as I said earlier, the energies were too high and it is impossible to form bound elements, bound nuclei. So, even if you bring a proton or neutron or some protons and neutrons together, they will be hit by a photon of reasonably high energy and they will break. So, you have to wait till 3 minutes after the Big Bang till this nucleosynthesis happens. So, this is the time the first nuclei in our universe form. Again remember the time, this is roughly 3 minutes, few hundred seconds after the Big Bang. Okay. The energy scale we are talking about is a few hundred keV, these are sub MeV scales, few hundred keV scales, somewhere around that. You have to wait for some time for the neutral atoms to form. You have already formed nuclei, and the next step would be to get the electrons bound to this nuclei, so that we have neutral atoms, let us say hydrogen. For that, the temperature needs to go down such that the energy scale becomes of the order of eV. This happens somewhere around few 100,000 years after the Big Bang. So, imagine the nuclei were formed after 3 minutes. So, you have to wait for a really long time, not just days or years, but few 100,000 years. Before this, what was happening is the electrons and protons were forming hydrogen, but they were immediately being broken down by photons. So, one would have kind of reached some kind of a equilibrium like this, but when the temperature becomes low enough, the reverse reaction, that is the hydrogen plus photons going to electrons and protons, the ionization basically becomes energetically disfavored, and that is the time you start forming stable atoms. So, that is known as recombination. This is also the time when the photons decouple from matter. So, before recombination or the formation of neutral atoms, the photons are coupled to the plasma, this electron proton plasma, through Thomson scattering. Okay. So, electrons the photons gets constantly scattered of the free electrons. Now, the moment you form atoms, the free electron density drops, because now the electrons have all got bound to the atoms, drops significantly, and then the scattering process becomes inefficient. This scattering does not take place so often. Then what happens is the photons are now not scattering of the electrons, so they just free stream. So, they free stream through the universe and they are everywhere. So, and as the universe expands, their temperature goes down. So, they cool, and this is nothing but the cosmic microwave background. So, clearly you see the fact that I termed the cosmic microwave background as something left over from the Big Bang is indeed true. Okay. So, this is happening, I mean this is very easy to explain in terms of Big Bang model and the expansion of the universe. You can also understand that because the photons were very tightly coupled to the free electrons, they are constantly getting scattered off. So, it is very easy to establish thermodynamic equilibrium at early times. So, that is why they are so perfectly black body, okay, and that is what we observe with the CMBR observations. There are various other things which happen, like the formation of first stars, the dark energy matter equality, and formation of galaxies, but that is something we will take it up in the later lectures. So, for the moment let us concentrate on the very early universe part of it, particularly from the beginning to the recombination. So, we will take out few of the milestones which are interesting and easy to understand. So, for the rest of the lectures we will work in units where we have taken h bar, c and the Boltzmann constant to be 1. So, that makes the expression look simpler, mathematics a bit easier, that is all. Consider the universe when the temperature is, let us say, less than 1 GeV. So, at this time particles which have mass larger than 1 GeV, like protons and neutrons, would have become non-relativistic. Okay. So, there are not enough energies. So, the energies of these particles will be dominated by the rest mass, and the kinetic energies are much less. So, they have become non-relativistic, and since their energies are less, they would not contribute significantly towards the energy density or the entropy of the universe. the energy or the entropy of the universe is mostly contributed by relativistic species, the species which are relativistic. As far as we understand, the only particles which would be relativistic at this time will be photons. Photons are of course always relativistic because their masses are 0. Electrons and positrons are also will be relativistic at the GeV scale because their masses are 1000 times smaller than that. And the 3 species of neutrino and antineutrino, again you can take them to be massless. They are believed to have mass now, but even if they have masses, they would be sub eV scales. So, when the temperatures are of the order of GeV, these neutrinos and antineutrinos will also be ultra relativistic. Now, what were the neutrinos doing at that time? They were in equilibrium with electrons and positrons. They were constantly interacting with electrons and positrons through weak interactions. For example, it may happen that electron and positron interact and give rise to a electron neutrino and the corresponding antineutrino, or then there are various reverse reactions which will also take place. Okay. So, to summarize, the neutrinos will be in equilibrium with the electrons and positrons. Now, this would remain like this, except that as the universe expands, the densities go down. As you know, the rate of interactions depends on the density. If you make the particles or the collection of the particles more and more dilute, it becomes more and more difficult for them to interact. So, as the universe expands, the interaction rates of the neutrinos, interaction with the other species, become lower, and at some point they become lower than the expansion rate, such that they hardly interact. Okay? You have to wait till the age of the universe for one interaction. So, for all practical purposes, they have become kind of free, they do not interact anymore. That would happen. For that, you have to know the interaction rates of these interactions. If you have some idea about weak interaction rates, you can work this out. It turns out that this interaction rate will become negligible at temperatures of MeV. So, at temperatures lower than MeV, the neutrinos are decoupled from the rest. So, they are not interacting, they are just moving freely, and of course, as we said, they are relativistic at this time, because neutrinos, even if they have masses, they are probably sub eV mass. So, at MeV scales of temperature, they can be taken as almost massless. Now, after this neutrino freeze out, what is happening is the neutrinos are free streaming, right, but the electrons and positrons are still interacting and are in equilibrium with the photons. So, electrons and positrons are coming together and producing photons, and then photons at some point are disintegrating into electron positron pairs. Okay, that is called pair production. Okay, so, this annihilation and pair production, forward and reverse reactions are happening. So, electrons, positrons and the photons are in equilibrium, and the neutrinos are going in their own way. Okay, they have decoupled. Now, since both this system, the neutrinos and this other soup of electron, positrons and photons, all of them are kind of relativistic, the temperatures of these components fall as 1 by A. Okay. So, the temperatures of the neutrinos and this photon, electron, positron plasma will continue to have the same temperature. So, even though they are not interacting, they will have the same temperature, because both the components, the evolution of their temperatures are the same. Now, at some point when the temperatures become less than MeV, as we said, the electrons and positrons annihilate and produce photons, that is fine, but the photons do not disintegrate and produce pairs anymore. Okay. So, only the forward reactions are happening. During this time, what will happen is the energies contained in the electron positrons pairs are actually transferred to the photons, because photons are not able to give that energy back to the electron positron pair, the reverse reaction has stopped. So, the temperature of the radiation is expected to rise. However, since the neutrinos have already decoupled, they cannot receive any of the energy released by the electron positron pairs. Okay. So, the neutrinos, their temperature will fall as 1 by A. For photons, they were initially falling as 1 by A. Then during this, when the temperatures are of the order of MeV, when this annihilation happens and the pair production stops, the temperature of the radiation rises a bit, and then again it keeps falling as 1 by A. So, after that, the neutrino and the temperature of radiation both fall as 1 by A, and whatever is the relation between them during the electron positron annihilation, that annihilation is maintained till today. One can actually do a full calculation, because in terms of physics there is nothing which we do not know, and you can actually work out the relation between the neutrino temperature and the photon temperature, the radiation temperature. It will turn out that the neutrino temperature is 4 by 11 to the power 1/3. How this factor arises will take some time to calculate. So, I will not go into that, but one can in principle calculate it and show. Now, of course, we know that the radiation temperature today is 2.73 Kelvin. So, that tells us that the neutrino temperature today should be of the order of 2 kelvins, 1.95 kelvins. So, in principle then the neutrinos actually form a homogeneous background just like the radiation, which in principle can be detected, but since the neutrinos interact very weakly, the background detection of this background is a big challenge, and also the fact that the temperature is smaller also is one thing, but on top of that, the neutrinos, they interact so weakly that it is very difficult to detect that background, but it is there. What is plotted here is the evolution of the neutrino and radiation temperature. As we said, at some point the neutrinos decouple. So, the radiation and the neutrino temperatures are equal, both falling as 1 by A, which will be early time. So, remember the x axis is scale factor plotted in some units, a y axis is log of temperature. Early times, both neutrinos and photons have the same temperature. At some point, the photons tend to receive some extra energy because of this pair, the annihilation of electron positron pairs. So, the temperature of the photons go up, whereas the neutrino temperatures keeps on decreasing as 1 by R. It goes up, and then afterwards it again falls as 1 by A. So, you can see there is an offset, but both fall as 1 by A afterwards, and this whatever is this increase, the factor remains the same. And today we detect of course the radiation, but in principle we should have the neutrino background is also there, which has a slightly smaller temperature. Okay. So, that is something which is a prediction of the hot Big Bang model, and that is just coming by applying our particle physics knowledge to the expanding universe. Okay. So, this is something which we will keep on doing. We will keep on applying our standard laws of physics to the expanding universe and see what we understand about the evolution of the universe. The next thing I wanted to discuss is the primordial nucleosynthesis. As I said, most of the nuclei were synthesized during like a second to 100 seconds after the Big Bang. 3 minutes is a good number to keep in mind. The basic nucleus is hydrogen, which is just a proton. So, that is the moment the quarks and gluons formed protons, I mean we had hydrogen all over, hydrogen nuclei all over. Okay. Atoms will come later, by the way. Now, what about the next stable nuclei? The next stable nuclei is helium, that consists of 2 protons and 2 neutrons. Okay. So, you have to bring together 2 protons and 2 neutrons to form helium. So, how will that happen? So, to do that, let us understand what happens to the neutrons and how many neutrons do we expect in the in our universe. During the era where nuclear reactions are taking place, the protons and neutrons should partake in reactions, basically weak interactions like this. For example, a neutron can act with the electron neutrino and give rise to a proton and an electron, and probably the reverse reaction can also happen, and so on. Okay. So, the neutrons, protons, electrons, neutrino, antineutrino are kind of taking part in these kind of reactions. If the whole thing is in chemical equilibrium, which will be satisfied when the temperatures are larger than MeV, much larger than MeV, because lower than that these weak interactions become basically negligible, the reaction rate goes down and this equilibrium is not maintained anymore. But at early times the equilibrium is maintained, and there you can calculate the ratio between the neutron numbers and the proton numbers. The 0 superscript tells you that we are evaluating this expression under the assumption of equilibrium. What you can show is this is approximately given by exponential of minus of the difference between the neutron and proton mass divided by the temperature. Okay. It is easy to understand this, because what you can do is you can regard the proton as the ground state for a baryon and the neutron as the first excited state. Then this relation is just the Boltzmann distribution law, e to the minus energy difference by kT. Okay. So, that is what is showing up. We already know the mass difference between neutrons and protons, that is something like 1.29 MeV. So, in equilibrium this neutron to proton ratio will be somewhere around 20%, 0.2. Okay. So, the number of neutrons will be less just because they are massive. Okay. That Boltzmann factor comes into picture. Now, what will happen is once the temperature becomes less than 0.8 MeV, I mean at that point the ratio will be kind of frozen to this 0.2. Instead of working with this neutron to proton ratio, we can work with the neutron fraction, that is just the neutron number divided by the total number of neutrons and protons, and that you can show that in just when this nuclear reaction stopped, that ratio will be 0.17. Okay. That just comes from putting in this ratio into this relation. Okay. This definition of the neutron fraction. Now, if the neutrons are free, they will actually freely decay through this reaction where neutrons go to protons, electrons and an antineutrino. This has a time scale of somewhere around 887 seconds. So, then if the neutrons decay, then what happens is the neutron number will go down, and that will go down by a factor which looks like this. The neutron fraction will be 0.17, which is the value at decoupling, times the exponential factor which gives you this exponential decay, and that increases with time starting from the time of decoupling with a time scale of 886.7 seconds. Now, you can ask the question that if neutrons keep on decaying and by every let us say 900 seconds they become half, then by today you would not see any neutrons, okay? All of them would have gone. Actually, the neutron decay happens only when the neutrons are free. So, they can be halted only when a neutron gets bound to a nucleus. So, clearly now you have to make sure that the neutrons get bound to some other proton or something, so that this decay is halted. Now, the next simplest nucleus will be deuterium, which is just combination of one proton and one neutron. Remember, this is just an isotope of the hydrogen. Okay. This is unstable, but at least that is the starting point. If you can bind the neutron to proton, you can halt this decay. So, let us then understand the deuterium formation. So, deuterium will be produced when a neutron and a proton come together, produce a deuterium and a photon. In general, at high energies the reverse reaction also work. A deuterium can be hit by a photon and that can disintegrate into neutrons and protons. Okay. So, it is not easy to keep a deuterium stable. the formation of deuterium is very important, because unless you form deuterium you cannot form the heavier helium nuclei. So, to form helium nuclei you need deuterium, and that is essentially shown by these reactions. So, deuterium plus a proton will form 3 helium and photons, and then deuterium will come and couple with 3 helium and will form 4 helium, and then will give away that proton. Okay. So, this is 4 helium, by the way, this is a typo again here. Now, as we said, the deuterium is easily destroyed because of the presence of large number of photons. The number of photons, remember, goes as T cube, because they just behave as black body spectra. So, to keep the deuterium stable, so that the photons cannot come and break it, what you have to do is you have to make the temperature small enough. How small? You have to get the temperature to somewhere around 0.07 MeV, mega electron volts. Unless you do that, you cannot keep this deuterium stable. This temperature occurs around somewhere around few hundred seconds. By this time the neutron fraction would have decreased, because neutron fraction would just keep going down, right. When it decoupled it was just 0.17. By the time you form deuterium it will come down to 0.12. Okay. The moment you start forming deuterium, no more neutron decay is allowed. So, now you see, although the neutrons form somewhere around 4 seconds after the Big Bang, however, one has to wait till few hundred seconds till first deuterium to form, and then once deuterium forms, the formation of helium is then straightforward. So, one has to wait for a few minutes for helium to form. The fact that helium formation cannot progress right after the neutron is because of this deuterium, and that is known as the deuterium bottleneck. So, even though you have protons and neutrons in the universe, you are not able to form helium. So, helium formation time is somewhere around, as I said, 300 seconds. So, all the neutrons which survive till this time will be actually taken up, will be assumed to be used up to synthesize helium. A very small fraction will still remain and will be used for rather heavier elements like lithium and all. And so, for simplicity what you can do is you can assume that there are n number of neutrons and they combine with n same number of protons. So, the number of heliums that will be produced will be n by 2, because each helium will need 2 protons and 2 neutrons, and the rest np minus nn, because the number of protons is higher than the number of neutrons, they will remain as protons, which are just hydrogen nuclei, right. So, now we can work out then the helium mass fraction. So, the helium mass fraction is 4 times the number of helium atoms divided by the number of neutrons and protons. This you can show that will simply be the 2 times the neutron mass neutron fraction. Neutron fraction when helium was forming was 0.12. So, helium mass fraction will turn out to be 0.24, and that is actually very close to the measured value. Now, you also see the point, the importance of deuterium bottleneck. If deuterium bottleneck was not there, then you probably would have formed helium right after the neutrons were formed, and that time the number of neutrons were larger. So, you could have actually found much more helium than what we observed. The fact that deuterium bottleneck happened brought down the helium mass fraction to 0.24. Okay. So, actually what I have been trying to give you is a flavor of how nuclei form. So, the actual calculations are slightly more involved. What you need to know is the reaction rates of all the nuclear reactions, and then you have to write appropriate differential equations to solve for the evolution of different species of nuclei, and they will be like a coupled set of differential equations, many differential equations. Very sophisticated codes have tens of such differential equations. Then you put it through a computer and solve it, okay. And they are being done routinely. This is one such plot which shows various mass fractions as a function of temperature in the x axis or as a function of time after the Big Bang. For example, let us look at the neutron fraction. So, the neutron fraction has some value at early times, and then it goes down because neutrons are captured, free neutrons are essentially captured in nuclei. So, you do not you are left with very little free neutrons at late times, right. Now, what about for example, helium? Helium at early times there are no heliums because it is not possible to form helium. Then at some point you start forming helium, you form, and then it achieves a stable value which is somewhere around the 25% which we are talking about. Now, helium formation, as we said, is very closely related to deuterium formation, which is this 2H. So, look at this green solid curve. Deuterium starts forming, and you can see deuterium formation actually peaks somewhere around few hundred seconds after the Big Bang, somewhere around here. But the moment you form deuterium, these deuterium are used up in helium. So, right after it peaks, it falls down because now the helium formation has started, right. So, deuterium abundance goes down, and then it hits some kind of a stable value, and so does helium. The full calculation will give you values for all other species like 3 helium and the other isotope tritium, the other isotope of hydrogen, and then slightly higher order elements like beryllium and lithium and so on. Okay. So, these are nicely calculated through these models. Once you have done that, what you can do is you can ask the question that can we measure these abundances in the later part of the universe, and whether we can verify whether this this picture, the model we built, the model I discussed, is correct or not. So, what has been plotted here in this curve is in the for example, if you look at this green solid curve, it gives you the helium mass fraction as a function of baryon density. So, all these calculations will depend on how many baryons you put in the universe, because the reaction rates will change. Okay. The more baryons you put, some reactions will go faster, I mean reactions in general will go faster. So, some species will be created more efficiently, some species will be destroyed more efficiently, and so on. So, all these things will be function of the baryon density. So, you can see the helium mass fraction is a function of baryon density. Now, it is possible to measure this helium mass fraction from observations, and these observations tell you that the helium mass fraction varies between this point and this point. So, since we know that the theoretical prediction is something which is given by the green curve, this tells you that we to satisfy the observational constraints on helium mass fraction, the baryon density must be between this value and this value. Okay. So, that is something which we can learn from the helium abundance. In terms of fraction of critical density, which is nothing but the omega, it tells you that to explain the observations of helium, we need the omega baryon to be somewhere between, let us say, 2% to somewhere around 5%. Okay. Fine, that is from helium. What about the others? For example, let us like deuterium. Deuterium has a property that its abundance, the number relative to hydrogen is what is plotted here, actually decreases rapidly with increasing baryon density. Now, again it is possible to measure deuterium, for example, using something called the intergalactic medium probes. If you do that, the deuterium abundance gives you a range between this point and this point. That would tell you that to satisfy deuterium, I need the baryonic density to vary between this point and this point, let us say somewhere between slightly less than 4 to slightly less than 5%, that is the omega. We can play the same game in terms of 3 helium and, for example, lithium, and these boxes show the observational constraints for each of them. Now, suppose we combine up all the observational constraints, we see that this shaded region is picked up. Okay. So, that is how the game is played. You can ask the question that how do we actually measure the abundances? Now, after 3 minutes, 3 minutes after the Big Bang, the nuclear reactions are not possible at cosmological scales because the temperature has gone down, the densities are dilute. The only way to have nuclear reactions after that is after you form stars and the stellar cores undergo nuclear reactions, and then they will produce these various elements, and some elements will be destroyed and so on. In principle, if we observe at areas of our universe far away from galaxy, and if we can measure abundances of, let us say, helium, deuterium or any other element, those elements will be primordial. Not only that, you can, one can do much better. For example, people have observed galaxies where the metallicities are low, or unevolved old stars and so on, and they can also be used to constrain the abundance of light elements. Remember, this is combined with our knowledge of stellar nuclear reactions. These are very well understood. Okay. For example, we know deuterium cannot be produced in stars, only destroyed. There are other elements which can be produced in stars and so on. So, even when we observe these abundances, and we can actually interpret these observations properly because we know what could have happened in the stellar cores. So, with all this we get these ranges in observations for various abundances, and it turns out that if we combine all these observations of various elements, this region, this bluish vertical region, shaded vertical region is singled out, and that tells us that the value of omega baryons must be somewhere between, let us say, 4 to 5% of total matter. Okay. So, not only the nucleosynthesis model works, it also helps us to constrain the value of the baryonic density. Okay. So, this is how we go on and understand about cosmology. The next thing, which is, as we were saying, is interesting, is the epoch of recombination, where the nuclei or the protons, the simplest nuclei, the proton and electrons come together and form atoms. Now, that will happen when the temperature drops below the binding energy of hydrogen of 13.6 electron volts, because if the temperature is higher than that, the hydrogen cannot be bound. The solution can also be worked out by writing the rate equations, or in this case you can use the so called Saha equation derived by Meghnad Saha, for example, when the equilibrium holds. Okay. So, what has been plotted here is the free electron fraction as a function of redshift, which you can convert to scale factor if you want, or the temperature. So, you can see at higher temperatures, which means at early times when the temperatures are more than eV, the free electron fraction is 1, which means all the electrons are free, they are not combined to any atoms. As the temperature goes down, the free electron fraction decreases very rapidly. This is because now the electrons are getting captured in atoms. Okay. So, this is somewhere around that, this is the time somewhere where the first atoms which have formed, and the free electron fraction after that point would have dropped down very drastically. Great. Now, this in terms of times would have happened few 100,000 years after the Big Bang. So, as we said, the energies are small enough so that electrons and protons can bind together, okay, and form atoms. Now, before that, which is this green region, you can imagine the photons which were coming, they were constantly getting scattered of free electrons. This is the Thomson scattering, and they were doing this random walk in this plasma. At some point the atoms form. So, there is this red nuclei and the blue electrons, they have come and formed atoms. So, now this radiation cannot interact with the free electrons anymore and are free streaming. This is nothing but the cosmic microwave background which we observe, and this is why the cosmic microwave background actually is so significant for Big Bang cosmology. It is very closely related to the formation of the atoms. Let me again reiterate the fact that this cosmic microwave background, the photons are interacting quite intensely with the electrons at early times brings them to some kind of an equilibrium, and because of that the spectrum, the radiation spectrum is very highly perfectly black body. Okay. This also acts as what we call the last scattering surface. To understand that, look at this some kind of the evolution of the universe. This is at present, and suppose we are looking in the past. So, at very early times the Big Bang happened, then inflation, then formation of nuclei and so on, and at some, so till this time the photons were getting scattered of the rest of the matter. Once you form this atoms, the photons are not getting scattered and would have come to us directly from there without much interaction. This picture is very similar to when we look up at the sky and there are clouds. So, within these clouds the photons or the light is constantly getting scattered of molecules within the clouds. Once it comes out of the clouds, it just reaches us. But what do we observe? We do not observe the full depth of the cloud, we just observe the surface of the cloud when the light was last scattered. So, the same analogy, what will happen is when we see the photons, what we will observe is what the state of the universe was when the photons were scattered for the last time, and that is basically when the CMB started. So, that is why this is called the surface of last scattering. Now, with radiation we cannot directly observe the universe beyond or earlier than that. For example, we cannot observe the state of the universe during, let us say, Big Bang nucleosynthesis using photons, because after that the photons would have scattered so much that the memory of the state of the universe at that time would be lost. Okay. So, you can see this origin of CMB, where the CMB originated, is very crucial, because they are the first atoms formed, the CMB itself is originated, and then that brings a lot of information, and that acts as the last scattering surface. Beyond that, the universe is kind of opaque to us. Now, how does the CMBR look in the sky? For example, if you take a measurement of the CMB all around the sky, you will see that it is perfectly homogeneous. In fact, that is a very good confirmation of the fact that the universe is homogeneous and isotropic at large scales. It is homogeneous and the temperature turns out to be somewhere around 2.7 Kelvin. This, for example, is what Penzias and Wilson would have measured, and then Kobe went the satellite, when it went up, observed this. Now, if you just look at slightly finer scales, do not average it over very large scales. If you look at slightly finer scales, what you will see is that it is not really perfectly homogeneous, but some directions are hotter and some directions are cooler. Now, the delta T, the difference in these temperatures between the hotter and cooler regions are of the order of millikelvin. Remember, the temperature of the CMB is somewhere around 3 millikelvin. This is like 1000 times smaller. So, it is not like if you observe with a very insensitive telescope or if you do a very insensitive measurement, you will not see this inhomogeneity, but if you are careful enough, you will see this. Again, this was observed by Kobe. Now, this has a dipolar pattern. Okay, it is just hotter in one direction and cooler in the opposite direction, and this is nothing but this is a fact that we, the observer, the earth, our frame of reference is actually moving with respect to the cosmological reference frame in which the universe is isotropic. Okay. That is because we are moving around the sun is moving around the galaxy is actually being attracted towards the local group and so on. So, this is happening because of our local motion with respect to the cosmological observers, and we can also measure this local motion now. We know exactly in which direction are we moving with respect to this cosmological rest frame. Now, suppose we subtract this out. So, because this is nothing to do with cosmology, this is happening because of our motion, we will get back again the homogeneous part of the sky. But now suppose we look at more finer scales, and now suppose we are able to measure temperature inhomogeneities differences of the order of microkelvins. Okay. So, few tens of microkelvins. So, that is like 10 to the minus 5 times the original temperature of the CMB. You will find that there are many inhomogeneities. Ignore the central part. The central part has nothing to do with cosmology, but it is simply coming because of radiation from our own galaxy. So, this has to be subtracted out if you want to do cosmology. But if you leave that out, it seems there are regions which are hotter, there are regions which are smaller, these are colder. The inhomogeneities are not very large, please understand that they are of the order of fractional inhomogeneities are of the order of 1 part in 10 to the 5. So, they are really fine, but they exist in the sky. This was later measured much more accurately with more recent probes. For example, this is a sky map observed using a more recent satellite called WMAP, and a similar sky map exists for another satellite called Planck. Okay. They have gone in the sky and have measured these inhomogeneities to an extremely high degree of accuracies. They have confirmed that these inhomogeneities are of the order of 1 part in 10 to the 5. These inhomogeneities are extremely important because they actually act as seeds of all the structures we see around us today. Small inhomogeneities at early times during the CMBR would have grown and then would have actually ended up forming galaxies and clusters of galaxies and that large scale structures, galaxies coming together and so on, and all the structures we see around us today. Now, this is something which we would like to understand in slightly more details about these inhomogeneities in the CMBR. What do they imply? What can we learn about the cosmological model about our universe? So, this will take some time. So, this is something which we will take it up in slightly more detail in our next lecture. But to summarize this lecture, what we have learned is we have discussed the evolution of our universe at very early times, when the universe was hotter and then because of expansion it started cooling. There are various particle physics events happening all throughout, starting from neutrino decoupling to formation of nuclei to formation of atoms and the formation of the so called cosmic microwave background radiation and so on. So, let us stop here and we will carry on with this CMBR inhomogeneities in the 5th lecture. Thank you.